Good evening. Good evening, everyone. Please welcome Hunz that will tell you how to avoid a warranty of many other things by taking the thing apart.
Hello, so let's just start. The focus of this talk is on hardware and possibly with software black boxes. To be more precise, we look at non-desktop hardware with or without software. And we won't talk about analog stuff, because analog stuff is rather messy to me, and I have no idea of that. So we will have a look at digital components only, and yeah, why do we do this? We want to understand the functionality, and this is what hackers do usually. They want to understand everything, how does this stuff work. And in the second part, of course, we want to extend and or abuse the functionality. And examples of such hardware-software combinations are set-top boxes, the digital receivers for pay TV or free TV or, well, DVD players and such stuff. Then there are, of course, PDAs and simpler stuff like microcontrollers. You also find microcontrollers in smart cards, so they are quite equal. And one could also think of digital cameras as hardware, software, black boxes. There is a lot of software in today's digital cams, and just to make an example, one could modify the software to hide pictures. So if you take a picture and someone wants, hey, you took a picture from me, no, I didn't, and the picture is hidden somewhere, you just can't find it via the normal interface, but you can then read it out via the PC, would be such an example. Or if we talk of hardware, there is, of course, radio frequency stuff, radio frequency identity, and infrared transmissions. And these things are already here, and they nowadays simple RFID cards don't have some software, but they are quite interesting though. And yeah, that's why we have a look at hardware-only devices as well. The motivation of all this. Hardware-only systems are usually less complex, but they are widespread yet. You know the vision of ubiquitous computing, so there's a microcontroller in every single bottle you drink and such stuff. This isn't there yet. We are at some earlier stage where we have a precursor to ubiquitous computing in the form of hardware-only black boxes without software, and they are less complex, though they have impact on people's everyday life because they trust those black boxes. In fact, people consider everything not a computer as long as they can't play Minesweeper or Solitaire on it. And we also need to hardware to get access to software. So we need some kind of interface to interact with the software or to read the software out of the device. And so hacking those systems can be, the first point, serious fun. And the second point, it will lead to a more critical view of black box systems, and we consider this a good thing because people don't like voting computers then anymore if they understand the lection. So let's have a closer look at the software black box. We have, of course, input and output and some magical processing, and we can look into the software and we'll find some patterns that help us. And these patterns are usually debuggers, emulators, and there are debug symbols in it. You will have function names and such stuff. And you have assertions. And you know the structure of some code, for example, of cryptography algorithms. You can easily find the S boxes and such stuff. So this helps when taking apart software black boxes. But without those helpers, it gets messier. And the first assumption we have to make is one has access to the firmware. We can't look at the firmware when we don't have it. So the first question is, what do you want to do with the system? Understanding everything works only for very small scale systems. And then you can look for an answer to that question by looking at the hardware interfaces that are involved in that process of interest that you want to look at and you want to understand. And then you slowly go the way from the input to the output and write down what the thing does. And and you often jump between input and output, and then somewhere in the middle you will find the last piece or so. Okay, that's the theory. The practice is hard and awkward work, and it takes hours, days, whatever, years. Here are a few firmware reversal hints. One stumbles above when reverse engineering software for embedded devices. The first problem is usually identifying the architecture. And this is very hard because one usually doesn't know all architectures. So you have to ask your friends, your ARM friend and your pre-PC friend, and you give them this chunk of piece and this chunk of code and ask, is this ARM, is this PPC, and such stuff. But one can also think of attacking this problem with some kind of software, so to put these patterns that emerge for different architectures from the software into a piece of software that just calculates the probability for each code. We are a bit experimenting with this, but there's no releasable code yet. Another problem is memory remapping. So you will find, for example, a usual application of this is in ARM computers. The jump table for the interrupts is at the start of the memory map, so at location 0. And you usually want to write your interrupt vectors for the software to it. But the ARM also starts at entry point 0. So you usually have the ROM bootloader at the same location. So what you do is you remap the RAM to, or some kind of RAM to this location, write your interrupt vectors, and it works. You won't see this easily in the firmware unless you have analyzed the complete remapping code. Also, there are uninitialized jump tables, for example, for the interrupt handlers and such stuff. And there are different CPU modes, for example, in ARM, for ARM32 and thumb mode. And the easiest way to deal with this is get access to the running firmware somehow. And getting a memory dump of this firmware, I mean by memory dump, not only the RAM, but also memory map peripherals. And so you can later play with them, and it's easier to analyze them. This can be done by patching the firmware to give you a snapshot via an interface you can easily write code for. For example, a serial UART. It is just slow, but you can let it run overnight. And you have to turn off the interrupts before, of course, or your snapshot won't be consistent. Back to black boxes. We have an input, some processing and output, and the input can be controlled to a certain degree, and the output can be observed. That's it. We don't have anything further. We can't, at home at least, we can't look into a chip and say, hey, it's doing A plus B. We can only guess this. So let's start with an easy example. This is it is a miniature radio-controlled car. You can let it drive on the table. I've got it with me if you want to see it and have a look at it. You charge it here at the remote control, and then you can drive on a table or such thing for a few minutes. Yes, let's have a look in this remote control. Here we can find the oscillator for 40 megahertz, and Well, the most interesting thing is, of course, this integrated circuit. It has TX6C standing on it. One can read this easily by just without any glasses. And so what can we do with it? There's only this IC, and the datasheet can be found via Google. That's a nice thing. This is often a problem finding datasheets for some more advanced chips. And there's one pin for every direction the car should drive into. And for example, here we have right, backwards, forwards. We have a turbo button and such things. And in the datasheet, you will also find that you just apply a 0 to that pin, and the car will drive into that direction. That's super easy, and you can directly put the remote control to your parallel port. That's what this cable was all about on the slide. And you can connect it to a PC via USB as well, with a simple software USB stack for the AVR microcontrollers, for example. Well, we did this, and so we are currently playing with computer vision, and we want to have some programs race against each other. And well, it's an application, and it's easy, and you just look up the datasheet, and you can start. Okay, so let's have a look into more complex devices and into some bus systems and so, because most stuff isn't that easy. We have serial transmissions. They are the most common, one can say, and they are usually lower speed. And the most common is RS-232. You find it on nearly all network components and such stuff. They are lower speed, and there's no clock, so they are working asynchronously. And you have a start bit, stop bit, a parity bit, but this is not necessary. And the bit rate is the baud rate minus start bit, minus stop bit, and minus the parity bits, or the parity bit. Yeah. It is used for communication between more complex controllers that run some kind of software. You usually don't use RS-232 when talking to hardware-only devices. And it's usually debug stuff. It's used for debug stuff. One might have seen the console hacking thing, so even the DVD-ROM of the consoles have RS-232. And one can patch the firmware with it. One wouldn't think of this, but this is the way they do it. The RX line, so we have two lines, one for RX, so for receiving, and one for TX for sending. And they are easy to spot if the device sends by itself. One just looks for the right sampling rate with an oscilloscope or so. We'll come to that later. And for TX, you have to brute force. So it's only easy if the device sends all by itself. If it doesn't, you have to guess the right baud rate and send. And it might answer if you hit the right baud rate and the right sequence of data. Okay. Brute forcing this TX line is a dangerous thing unless you add a resistor. So you calculate just how much current there may flow. This is usually 10 milliampere and doesn't harm any device. And so for 3.3 volts, which is common among most devices nowadays, this is just 330 ohms. And you just put this in series between your serial cable and the pin you want to try. Put something on your enter key and apply this to any pin you are suspecting. It's a serial. And you'll get some answer on RX if you're lucky. I found a bootloader for, not a bootloader, but a debugger in a Bluetooth stick that way. The RS-232 can be interfaced by the PC rather easy, but you mustn't forget the level shifter. So 3.3 and 0 is the 0 and 1 in the embedded devices, but your PC speaks plus minus 12 volts or so. And one uses level shifters for this, but today we have USB to serial cables, and we often don't have serial devices anymore. And for some of these cables, the cheapest solution are mobile phone cables you get on eBay for older mobile phones. You don't need the level shifters then. You get them for about €1. And but you have to be careful. The quality of these devices at higher baud rate varies. So if you use 150 kilobits, they often lose the synchronization. And but you don't need level shifters. Well, next example, I2Z, and this is also rather common, and it is low to medium speed. So the specification, the latest is until a few megabits, as far as I know, but I haven't seen this yet. And we have a clock line and a data line, so it's synchronous, and the data lines are just pulled up, and then by the circuit that wants to send data pulled low. And this way you can put multiple devices on the same bus, and they, if they start sending at the same time, it will help no one. Is also the way one interfaces smart cards, since the I/O is bidirectional. Okay, this is a master-slave bus, so the master sends data to the slave, and the slave may answer then if the master wishes so. And it is used for communication with rather simple ICs, but it is also often used for communication between several microcontrollers. And so there can be a firmware at the end, some kind of software at the end of the square C bus. The slave is addressed by an ID, which is 7 or 10 bits, though I haven't seen 10 bits yet. And there are different IDs for different types of integrated circuits. We'll have a look at 2 examples in the next slides. And the master is often implemented in software. So if you see if you reverse the firmware and see some kind of weird bit banging with 2 bits, this might very well be I2C. SDA is sampled on the rising edge. Well, okay, there's special bus states, start, stop, and acknowledge or no acknowledge. There's a start condition with, as you saw, SDA is sampled on the rising edge of SCL. It is changed while the SCL is low, and the special bus states violate this condition. So while the clock line is 1, SDA has a rising edge, so it goes from has a falling edge, so it goes from 1 to 0, and the stop condition is inverse. Okay. Here you can see it. Oh, it looks better than I expected. Here you can see the start condition. Then we write to device 88, and we write to register BA, and we write the value 30. And we get an acknowledge from the slave, and we stop the whole thing. Well, this bar here isn't necessary, but there are some weird implementations out there that work as well. And the transmitter sends as long as the receiver asks, and the last bit of the slave address is the read or write bit, so we have a 1 for read and a 0 for write. Here we have a 0, so we are writing. Write means the master will send, and read means the slave has to send. Now there's something a bit odd about I2C. So you can't just tell the slave, I want to read from address 5, and it will reply with this address, but you have to do this read from address or register X by doing a dummy write to that address and aborting before sending any data. And then you can just read from the device, and it will reply with the data then. Logging can be done with the parallel port when it's rather low speed, and a microcontroller or other possibilities have higher speed. But we'll come to this later. Okay, here we have an I2C serial EEPROM. It is used to store data, and they are usually named 24ZN, where N denotes the kilobits, and the slave address is usually starts with C, and it can be configured via the. But that's not important. It's used to store configuration for the device, vendor IDs. The MAC addresses of Ethernet cards are usually stored in these things, and you can also store code in this. They are easy to interface and easy to sniff. And for example, here is a except from a dump from a serial EEPROM from a DECT station. You can find the PIN number in binary coded digits form if you forget it, and you also find the MSN numbers in there usually. Okay, next example for I2C. In set-top boxes, there are video encoders that do some output conversion between VGA and such stuff to something a TV likes, so PAL or NTSC, and they apply microvision signal, so you can't record it. One can just disable this thing by writing to the right register, and usually they don't publish what bits you have to toggle to disable microvision copy protection, but often they publish the data sheets for similar types that don't have microvision support, so you just look for some reserved bits that are written to 1, and you turn them off and microvision is off. You also can enable PAL output for NTSC devices, vice versa, and such stuff. Here's some excerpt from a Microsoft Network TV station set-top box. Yes, from this video encoder. Okay, next example. I'll do this one short because it's you can read this better on Wikipedia or so. It's rather high speed and it's SPI. And it can't be found that clearly like I2C. You have a clock, master in, slave out. That's a great advantage about RS-232. I always get the lines wrong, and you don't have this problem with SPI since the names are clear. And master out, slave in for the reverse direction, and slave select to tell the slave we're meaning it. And one can find this the clock signal usually by the scope or so. It is usually a rather high-speed thing, about several megahertz, and they are usually doing 8-bit transfers there. It is implemented in hardware, and it is a bit similar to I2C, but higher speed, and it can be implemented in logic more easily. Examples are radio modem ICs, so you'll find the SPI bus in your Sputnik. If we hadn't the datasheet for the radio chip, we could just sniff here and see what registers are written to and read from. SPI bus can be also used to interface SD cards, analog digital converters, in-system programmers for microcontrollers and such stuff. But there is no simple solution for high speeds. But one can use a microcontroller that has 2 SPI interfaces and put the MISO and MOSI lines to 2 MISO lines of that microcontroller and put the SPI into slave mode and just sniff them. But you also have to get it into the PC some way, and this is another problem we'll come back to later. Next example, we have an ink cartridge. You might have read it in the abstract. They are usually equipped with some kind of chip nowadays. Some vendors call it anti-refill device, some call it user protection device or something like this. And to protect the user against evil ink, of course. So, well, I think I know what I'm doing, and when I want to mess up the printer I bought, I'll just do it. And let's look how. We have a serial transmission here. One line is missing here, the reset line. My oscilloscope only has 2 channels, and I didn't want to write code for a microcontroller a few days ago. So the reset line is inverted, so if it goes from 0 to 1, the reset state is aborted. Yeah, it's synchronous and it runs at 62.5 kilohertz. This is a bit similar to I2C as well, and you can, but it is too fast for sampling with the parallel port as long as a usual operating system scheduler is running. The printer is master, cartridges are slaves, and after reset, one has there are, as I guess, there are 3 bits in the cartridge address. Well, I can't say this for sure because I don't have a photo printer, so I only have 4 cartridges, and the first bit didn't toggle for any cartridge. Then after these address bits, one has 1 bit for read or write, and one can write arbitrary data into that chip, so you can use it as data storage, key storage, or whatever. If your ink is empty, because we don't refill it, of course, and but one has to use a lower frequency than for reading because this takes up more time. Okay, so one just dumps the contents of the memory when one buys a new cartridge and writes it back once it's empty. A fake chip is also built within an afternoon using a custom, using a common microcontroller. Okay, let's have a look at wireless transmissions. Usually one uses 433 or 868 megahertz. There are devices as doorbells, main switches, dimmers, air pressure sensors, temperature sensors. They are sold as home weather stations, and there are also fire alarms and burglar alarms. Hello. They are using different encodings. Manchester and no return to zero can be used, but usually it's something with return to zero. You can also look that line codes up at Wikipedia. This is without the scope of this talk. And there are usually IDs, and they are a few up to 12 bits, and there are simple encoders and decoders like PT2272, and you can also find a datasheet for that. And okay, so everything is documented as far as these chips are used. One can easily sniff 432 megahertz by buying a $5 wireless doorbell and finding the right wire to attach a sniffer to. And this is a good wire here because it is, here the signal comes directly out of the analog circuit and goes into a Schmidt trigger to digitalize the signal, and you can easily hook it up to the sound card and set some kind of trigger value. And if you get a signal that's stronger than this trigger value, you can just log this and later analyze it in a wave editor like Audacity or so. And another very valuable sniffing helper is your ears, and you can just attach it to the microphone input of your notebook so you can hear the signals, and this is very fine for scanning your neighbors and their thermometers, and so you just hear the beeps, and you can look for the best reception area and put your notebook there and sniff a bit and build your own temperature receiver for his temperature sensor. Okay, well, I got a wireless device, and I got it for $40 about, and it's a wireless alarm system. So let's hack this one. How can we do it? Well, let's try it MacGyver style, since it looks rather cheap. I tried this, but it didn't work. So we need a more sophisticated hacker tool. A paperclip doesn't do it. Here it is, the sophisticated hacker tool. This works very, very reliable, and the data from the sensor doesn't get to the base station any longer, and the base station is just dumb. And, okay, so the wireless sensors are crap, but the alarm system is protected against the denial of service. So if you take it off the wall, it will sound the alert. Yeah, that's okay. So let's have a look at the signal. Here we see two signals. It has a 4-bit ID, and we can switch the ID bits via dip switches. Here one can see those bits, and I switched one, and one can easily see its Manchester code. This is a screenshot from Audacity, and it is just sent in case of an alarm event, so there is no heartbeat signal or such from the sensor. This is why our hacker tool works. But there are also ones available with heartbeat signals, but they are sometimes in the range of 10 minutes or so. So if the burglar can break into a house within 10 minutes, the alarm is completely useless. Well, it was boring. The fun wasn't worth the $40. So let's have a look at some other stuff. There are a lot of infrared transmitters and receivers available everywhere, and this is usually done by applying the data to a carrier frequency. And the common carrier frequencies are 30 to 38 kilohertz or 445 kilohertz, and the sniffing effort depends on the carrier. So here we can see a few receivers. This is usually this is a receiver that is used for 30 to 38 kilohertz. It does already digitalize the signal, and you get a 0 if the carrier is there, and 1 if the carrier is missing. So this is, you can just read the signal very easy. And this is the same for 445 kilohertz, and here we have an infrared diode from which you get raw analog data. And this is rather hard to handle because you have because you need to amplify this signal by a great deal. And yeah, this is all done in this IC usually. But you have to use such a diode if you don't know the carrier frequency, and you usually don't know it when you see a signal for the first time. You could of course just try a few carriers. Okay, they can be used for asynchronous serial transmissions up to 2004 kilobaud. So one could easily put the RS-232 interface just to over infrared. One can transmit it over infrared, and RS-232 is a no return to zero interface, but that doesn't matter since we have the carrier here, and yeah, and the automatic gain control will handle it. So if you want to see infrared transmissions, look for daylight filters. You can see them; they are black, like here, or dark red. And where can you find these transmissions? Well, in hi-fi remotes, usually the most common application, remote-controlled vehicles. There are flying helicopters available, and there are also interfaces, infrared-based interfaces to cigarette and drink automats, and the infrared transmissions are used in public transfer. So if you see omnibus with those two circles on the side, these are infrared ports, and you can spot these things rather easy with your cell phone cam. So this is a picture taken with my cell phone camera. The infrared gets a bit through the filter, and you'll see the transmissions there. Well, you see that there is infrared light, but you can't record the transmissions because 25 frames per second aren't enough. Okay. Other infrared devices, here from Starbucks, flat, here from the radiator, it counts the heat, and one gets a bill depending on the amount of heat one used. And this is a water meter, and it looks to me that it also has infrared in it, but it could also be 433 or 868 megahertz. So these devices, both of those devices, are also available as wireless versions. So janitor or so can just pull them while going through the house, or they can also be resetted via wireless transmissions, I should say. But we won't do this, of course. Okay, let's get back to more complex devices. Memory interfaces, they are parallel interfaces, and they usually have 8, 16, or 32 data bits. One also has control lines like read and write, and there are sometimes also lines to extend the access to add custom wait cycles, and for slower I/O devices, for example. This is how PCMCIA works, and if you want to have a closer look at the PCMCIA stuff, you can have a look at the Afrolus link I added in the pentabaf, so I added at the talk side. But let's get back to the flash memories, and this is where the software for set-top boxes, PDAs, and all this stuff is stored in. One can use software to dump it, so there are no costly hardware needed to do this thing. But they are high speed, so when tapping the bus is rather complicated. But as long as you control the whole thing, you can give the speed, and you can do it with a parallel port. This is what I did here with a flash memory from a handheld mobile, whatever, it's kind of BlackBerry style. And you just read the data sheet and implement the bus in software, and then you can read it out. Of course, you have to do some soldering, and you have to get some practice with this. And also a hot air station is rather useful, but they are already available for $60, so you can do this at home. Okay, so what do we use to interface hardware? Well, for the analog part, to get a first impression of the signal, oscilloscope is very useful, but it is also expensive. So there are a few low-cost substitutions. For example, for this 333 megahertz receiver, we used a sound card, and to get a 48 kilohertz sampling rate, or with the high definition sound cards, you get a 96 kilohertz sampling rate. So this is enough to get 24 kilohertz signals clearly, or 97 divided by 2. The ADC of a microcontroller is also a useful thing. Example, this A4R 8-bit microcontrollers, they can do 666 kilohertz sampling rate, and the ADC clock is half the clock of the system, and it needs to have cycles for one measurement. So this is why there are 666 kilohertz sampling rate. It is very nice because you have 10 bit, and you also have 200 times gain. This gives you a precision of a few microvolts, and you can just put the infrared diode to this ADC and add some trigger point for detecting the signal, and add another value, and you say 0 is below this value and the 1 is above this value, and you have your digital signal. For example, one can just hook such an infrared diode, I have one with me, to such an A4R microcontroller, and sniff the TV begun thing, and just build his own without buying the components. Back to the digital part. There are logic analyzers, but they are very expensive. And you can put something together in most cases. And another advantage of putting something together yourself is that every problem is different, and so you need a different solution. And this makes custom hacks necessary. Okay, the parallel port is very slow. You can do only a few kilohertz sampling. While a scheduler is running, there are some hacks to turn interrupts off and such stuff, but I think this is rather messy. So I am using external logic, but you can do 2 megabytes per second with ECP-enabled parallel port, and you also get DMA there, so this is a very nice thing. It is also faster than full-speed USB. You can use a microcontroller to do the real-time sampling, of course, and a CPLD or FPGA if necessary. The AVR 8 bits are slow but easy to program, and they are great for hard real-time because you know the exact time in cycles every comment takes, and there is no cache and no complex pipeline. So you can just say this branch will take 2 hours if taken, 2 cycles if taken, and 3 cycles if not taken, or whatever, and just have a look into the datasheet. This is another thing with the ARM microcontroller. They are very fast. They are 32-bit. You have lots of SRAM up to 64 kilobyte, and they are fast, and one can not do hard real-time that easy because there are pipelines and caches, and yeah. You have to use some sort of hardware support then. For example, timer-based sampling or such stuff. Also, when grabbing data and transmitting it to the PC, use a ring buffer and use an overrun indicator. Or you'll analyze the data just to find out, damn, there's one sample missing, it's all messed up, and you wasted your week analyzing that. Data can be transferred via RS-232 if it is below or equal to about 9 KB per second, and full-speed USB gives you about 1 megabyte per second, and high-speed USB gives you below 60 megabytes per second. This can't be said very easily. The exact speed you have depends on the controller and such stuff. You have to test it. One can also use the hard disks interfaces to get data hellish fast into the PC. So parallel ATA gives you 130 megabytes per second. So you can just emulate a hard disk using a bit of gluing logic like FPGA, a small one. Maybe it is even possible with it should be possible with a CPLD. And you can also use serial ATA, but this is low voltage differential signal, and this the signaling is a bit messier here because you get several gigabits, and if you have a 90, the routing the lines is very complicated then. So there's no interference. Ethernet doesn't make any sense because it is very complicated, and with 100 megabit you only get 12 megabytes per second in the best case, and you have protocol overhead and all that stuff. Okay. Questions you should ask yourself first before doing anything. How much data do I want to log, and how many signals? No fast interface is necessary if you can put the data completely into your buffer space. This is true for the ink cartridges. I just used an HVR to do this thing, and I just used the internal SRAM, and I added a button to give me the data via serial interface. And the next thing is, what's the maximum speed of the signal, and how do I get an appropriate sample rate to digitalize this signal, or to grab this signal? And depending on that question is the question, what interface do I use to transfer the data to the PC? Of course, this has to be fast enough. We'll see some sort of solution in the next slide. And to answer this question, the how much data question also. And okay, the next question is, how do I store the data in the buffer? One can often compress the data a bit. And how do I send the data to the PC? The question is, do you have enough processing power to store it in this particular format? And do you have enough throughput to the PC to send it in this particular format? For example, I2C, we have 2 lines, so we can just send a byte per sample. This makes 6 unneeded and unused bits. So one can put 4 samples into 1 byte, and yeah. But your microcontroller has to do this, and you have to count the cycles to find out if you have enough processing power to do this. For the ink cartridges, it is 62 kilohertz for the signals. So and the HVRs can run at 8 megahertz, and this gives you more than 100 cycles to do these things, and this is by far enough. Okay, the answers to these questions are count the transitions for how much data. You can use the hardware counter of a microcontroller if it is fast enough, and if it isn't fast enough, you have to build a hardware counter using some other logic. This means CPLD or FPGA. And the next question is maximum speed of the signal. So the time between 2 transitions within the signal. So if the signal goes from 0 to 1 and from 1 back to 0, these are 2 transitions. And we have to measure the time between these both to decide how fast it is. One can use the hardware timer of a microcontroller if it is fast enough again. For the HVRs, hardware counter and timer are shared. You can just switch them. And if it isn't fast enough, one has to use logic. This again means CPLD or FPGA. And the problem with these 2 answers is that you won't know whether you really sampled, whether you really know that it's fast, that you did it fast enough. So if you glue the microcontroller with 8 megahertz to 80 megahertz bus, it will just miss all those things. So you will need to use very fast logic to make very sure you get it fast enough. In general, fast and simple stuff is a job for hardware. Keep it as simple as possible if doing something in hardware, because it will take a lot of space, logical space, and a lot of time fiddling with this, and do the messy, slow stuff in software and the complex stuff, because you can easier fiddle with that stuff. Don't panic. This is a bit of code for an FPGA or a CPLD to implement such a timer that measures the time between 2 transitions, and here it gets a clock signal, reset signal, so you just reset it in the beginning, and then the clock is used for the timer, and it will here look for signal changes, and if there is a signal change, it will set back the timer to 0, and if this timer was below the previous minimum, the new minimum is the timer. This timer value here isn't applied now. It is applied after the run of this process. This way I can write this here, and the timer value is still valid and not 0. Okay, that's just a bit of VHDL fiddling, and yeah, just to give you a short idea. And we also want to protect our timer against overruns, because we would get wrong results then. So this is a saturation timer. Here is the interface. So you need some kind of interface to get the data out of the CPLD or FPGA again, and this is what DO is for. I didn't add the code here because this is rather easy, and well, the most important is this one. It is only to give you some sort of idea. And yeah, here you have the clock for the timer, and yeah, run, reset, signal input. Okay, the speed of all this is about 66 megahertz. With CPLD you get for about $4 from Reichelt, for example, and you can solder this one very easy yourself, and it has and after putting that timer into it, you have a 50 to 75% logic usage, so it is nearly completely full, and this is not that fine, because you usually want to monitor more lines at the same time, but this way you have to do it with each line and then move to the next line, reset the device, and do it again. Yeah, but there are also FPGA boards available for about $100. You get a few hundred times the gates you have with a CPLD when using an FPGA. Okay. So how do we analyze the results? Custom visualizers for the signals can easily put together via using STL-GFX extension. And, well, it is hacked together very fast. And if you want to write a picture, you can use the portable bitmap format. This is just an ASCII header and raw data. So you just write it there, and okay, you can load it in every Unix application. And print the stuff that drives you nuts to paper, take it with you, sit down somewhere and work with several colored crayons on it. And this is the best way to deal with this. Okay, so let's look at the conclusion. There are a lot of simple proprietary devices out there that aren't yet ubiquitous computing, but some kind of precursor. They have little to zero security features because hackers are computer guys and no one will notice ever that we're doing here. So hacking them is simple and funny. Do it. Before the questions, if there are any, this is a picture of an Atmel ARM controller. This is an Atmel HBR controller. ARM, HBR. Just to give you a picture of the sizes, you have to solder them. But there are also adapters you can put them on, and this again is very nice to solder using hot air. Okay, that's it. Questions? No questions? Thank you for listening.